All right, so I'm gonna maybe try to redo this demo. I did do it, but then I guess I must have deleted it. So I'm gonna post a video for you of some other guy doing it. I think the way I did it might have been a little bit better from like it's an experience perspective. But what I'm gonna talk about here is interference between sound waves. And so think back to the linear medium when you sent two pulses at each other at the same time. You can get them to interact and they can add up while they're in superposition. Then they pass through each other. Right? And then you get a big wave here of twice the amplitude. But if they were on opposite sides, while in superposition, cancel each other out. And then they pass through each other as if they didn't even interact. All right, so that's a phenomenon that we've seen on the linear medium, like a slinky or a string, and we want to think about sound waves a little bit more. So sound waves are a little bit different because they're definitely a different type of wave. The medium is air. They travel three-dimensionally everywhere, and essentially, if you are thinking about a speaker is probably the ideal device to emit a sound wave. It emits it out and it's going to travel like that. But it's a longitudinal wave of alternating high density regions and low density regions. And so if you're looking for the wave-like nature, it's hard to see it in the longitudinal representation of a linear slice of a sound wave. But if you think about air pressure here, air pressure is oscillating between high and low pressure. So you got high pressure here, low pressure here, high pressure here, low pressure here, high pressure here, and so on and so forth. So basically, we want to think of the compressions as our crests. And so when you think of a sound wave, if this is a point and we've got a bird's eye view of, let's say, a speaker emitting a sound, it's going to emit it out in a three-dimensional fashion. And I'm representing the crests of each of the waves as the wave radiates out. The crest should be equally spaced because their wavelengths are determined by, let's say, the frequency of the speaker itself. So everybody should be hearing the same frequency here. And this weird phenomenon of interference does occur in sound as well, meaning that if you've got two speakers playing the same sound, there's a good chance that you're probably going to hear something be twice as loud, and that makes perfect intuitive sense. Where it's a little bit more confusing is that you can actually find a place where those sounds are actually canceling out, and it might be relatively low volume because you have some destructive interference occurring. So if you have two sources playing the same frequency, source 1, source 2, source 1's going to emit waves that are traveling out like this. It's going to reach everywhere in the room. And I'm doing my best to kind of try to draw these equally spaced, but it's not the easiest thing to do. Source 2 is also doing that. Same frequency, so it's emitting its waves around. And like I said, I'm going to do this demo over, probably outside tomorrow if I get a chance. And what you should be able to do is you should be able to walk around these two sources, and there's a loud spot and there's a silent spot. Now you can try this at home. I'll bring up the online tone generator in a little bit just to show you how you could do it. But basically, if you walk to this point right here, this is a point right here where the crest of one meets the crest of the other. This right here would be loud because you're getting constructive interference there. On the other hand, if you ended up going where the crest of one meets the trough of the other, this right here would be a soft spot. So as you walk throughout these two speakers here, some points are loud and some points are soft, and you're going to literally hear the sounds cancel out. And it's a lot better if you do it in person than on speaker, but you know, it is what it is. There's a program that you can test it on. Now this is only going to work if you have actually two sound speakers. So, you know, if one of your speakers is broken, don't even bother trying to do this. All right, so if you go to online tone generator, that is a decent app that's going to allow you to play a sound, and you can literally, I would actually recommend maybe 1,000 hertz. If you play 1,000 hertz and you're playing it from one speaker and another speaker simultaneously, you're going to hear that, right? And then what you can do is you can walk through the room and see if you can hear the sound oscillating up and down. You might also be able to find a quiet spot, and sometimes, ironically, the quiet spot is very close to the speakers itself. You can fool around with different frequencies here. You can play something like a lower frequency if you don't want to be as annoyed, but I think it might be a little bit easier to find those spots if you are looking for the or if you're playing the higher frequencies. So there's a reason why this happens, and it's really you're putting yourself at a point where crest is meeting crest or crest is meeting trough. And I should actually also bring up the point that, like, if you did this point right here, it'd be trough meeting trough, and that would give you constructive interference as well, because that is analogous to two waves approaching each other on the opposite side, and they're still going to add up to a large amplitude just to the bottom end of it. All right, so you'll hear loud spots and soft spots, and the way this happens is basically depends upon path length difference. So these waves travel a certain distance, and the distance that they've each traveled is going to determine whether you're getting crest, trough, or something in between. And what we want to do is think about those distances. So I would call this distance right here R1, and this distance right here R2. That's how far away your location is from the speakers themselves. And basically, delta R, the path length difference, would be R1 minus R2. And we'll just put an absolute value around it so that it's definitely positive. And basically, if you have delta R equaling some multiple of the wavelength itself, where M will equal 0, 1, 2, 3, and on and on and on, you're going to hear a loud spot. There's constructive interference occurring there. If delta R is off by half a wavelength, then you're going to hear destructive interference. Now you can have something in between where we wouldn't really consider it constructive or destructive, but basically there's probably an infinite amount of points around here, or just a very large amount, where we can either get the sounds to cancel out or add up. So in another video I'll show you another way that we can investigate how sounds can interfere with each other.